I think. All right, we're going to go over, you all have this in front of you, the sample one from 2012, the multiple choice section. I'm not going to go over every single one, but a guy like the first three requires you to have an idea about atomic radius, the periodic trends. You're okay with that. Let's go to 4. If we look at 4, and we'll see that this is a kind of question on the test that I got right away, because I remember doing these same exact problems with you guys when you were doing organic. If you remember, the guy that's the correct answer here wants to know which of these species is not planar. Y'all watching that? Y'all see that? You reading that? Not planar. This has to do with the Vesper Theory. Okay? Now, I want to review Vesper Theory a little bit with you to give you the correct answer. I knew right away that it was going to be E, but I'm a chemistry teacher. And I know that I asked that exact same question, PCl3. Oops. PCl3 was the exact same one I asked you in probably more than one place, both as an example and in one of the lab questions when we did the model lab, putting the models together. But I don't expect you could possibly remember that. So I want to kind of go through here why the correct answer is this, and also why it's a bad question. Knowing that you're not a chemistry teacher, knowing the idiots that wrote this test, all right, made out where, yeah, anybody who's taught chemistry sees that right away that's not going to be planar. But you guys would have to draw it out. You guys have to draw the electron dot notation for every one of those guys, starting from needed, available, shared, and it would take you 10 minutes to do that. To do the electron dot notation for those 5 compounds, it's going to take you 5 minutes at least. You have a minute and a half. You have 90 seconds to do it. Obviously, you can't do it. Now, the reason this guy's correct, I'll show you. Phosphorus trichloride's electron dot notation, I know, looks like this. Because I've done it so many times. And let's go over to Vesper Theory. The Vesper Theory says you ask yourself, how many things are bound around the central atom? How many things are bound around the central atom? Not 3, 4. Remember? There's actually 4 things bound around the central atom, 3 of which are actually atoms. Remember this? So you really have a tetrahedron. You have a tetrahedron with its top pulled off. So what shape is that? Triangular pyramidal. That may be coming back to you as I refresh your memory on it. But, I wouldn't expect, unless you did that one first, it happens to be E, by the way, just to throw one more punch at you. It happens to be not A, not B, not C, but the last one you would choose. It's ridiculous that they would ask this kind of a question to a student who has to do these from scratch. But let's just go over a few of the rules of the Vesper Theory, because they may not ask it in that hard of a way in the future, or they may ask it as part of the short answer question. We'd have more time. What if I've got this situation? What shape would that guy have? How many things are bound around the central atom now? 3. That would be triangular planar. That's planar. Which is why, by the way, the correct answer is not B. BF3 is planar. This would be BF3. B only has 3 electrons in its outer shell. And if you were to share those with an F, it would look like this, right? If I were to try to do it fast. If I wanted to do it with the needed available share, which I will do one of the harder ones, the first one, A, with that way. I'll show you how that works out. I would have to remember that boron's one of the exceptions, which, again, is just another dig they're throwing in there. It's, again, an unfair question. It's an unfair question because of time. It's an unfair question because it asks exceptions instead of the rules. And it's an unfair question just because it's in a multiple choice setting, and you just can't possibly, you'd have to do every one of these to do it. You guys, I see it because I've done it, but you don't memorize phosphorus trichloride is going to be pyramidal, triangular pyramidal. Well, that's, what if I have this? A, B, B. Oops, I just did B. What would that shape be? How many things are bound around a central atom now? 4. 4 things form a tetrahedron, but only 2 of them are atoms. So if I pull off 2 of those sides, what do I end up with? No, I don't end up with linear. I end up with what? If you want to see that, I should have had one of these out already. I'll get one out right now. Okay, here's your tetrahedron. Yeah, it's going to be bent. What you have is this. Okay, let's go back to the PCl3 one. PCl, Cl, Cl. with dots up there, with the pair of electrons up there. That's why it's triangular pyramidal, right? Well, if I pull 2 of them off, it's bent. That's water, H2O, or O, H, H, the way I would have drawn his electron dot notation. Some electron dot notations, like water or HF or HCl, for example, you could just draw without doing needed available shared, without using the actual basic rules of electron dots. However, I would suggest for a guy like the hardest one on there would be CO3 minus 2, I think. Okay? For that guy, you almost have to use it. Okay? You almost have to use the rules I taught you a long time ago. Now, how many of you remember these? You don't. You don't remember these. And it was only this year that we learned it. And we did use it for quite a bit of time afterwards, but I realized that's tough. Okay, let's take a look. Carbon, remember, the needed is basically to make everybody happy. How many do they need? 8. Most people need 8. What's some exceptions to that? How many does hydrogen need? Not 1. 2. I know the way I usually ask the question is, when I say how many does oxygen need, I usually mean, well, he needs 2 more than what he has in his outer shell. But here we're talking about the total number for an octet. So basically the needed would be 8 for him and then 8 for those 3. What's 4 times 8? 32. So you need 32 electrons. Remember this? How many are actually available? Carbon is in group 4, so he's got 4. Oxygen's in group 6, so he's got 3 times 6. What's 3 times 6? 18 and 4. Plus, you've also got a polyatomic ion, which throws one more curve at you of 2 more electrons. So what does it come out to be? 2 more besides the 22 is 24. So the total number of electrons that have to be shared are how many? 8, right? You subtract, okay, you need 8 shared. 8 shared electrons, they always share in pairs. Divided by 2 means there's going to be 4 bonds, 4 shared pairs of electrons. Now, here's a problem with the carbonate ion. Here, I've got 3 guys around him. I draw my skeleton structure. There's my 3 O's around here. But I got to share 4 pairs. What does that mean I have to have? A double bond. Right? Now, so you put the shared pairs in, and then you fill in the rest, so you get the total number of electrons available. Right? So you got, that it? That's all you can fit there, right? That gives him an octet. Right? Now, if you add them up, you'll find that's the correct number of electrons. Keeping in mind, you got minus 2, you should have 2 extra electrons on there, right? All right. So that's what this guy looks like. Now, I ask you, could you do this as just A, B, C, D, and E, and do all this in 90 seconds? Of course not. I'm using this as an example to go over with you because in the last year's test, there was an electron dot notation problem. It was in the free response, so you would have plenty of time to do it. This one, really unfair, completely unfair to do that to you. By the way, it also answers the question, how many things are bound around the central atom? This time, how many? Only 3, right? Remember carbon dioxide, one of the classic electron dot notations is carbon dioxide. You could do the needed available shared, but if you remember, it comes out to be this when you do it. Okay, it comes out to be that. How many things are bound around the central atom there? 2. What shape do 2 things get when they get as far apart as they can? Linear, right? Remember that? That's linear. Okay, so that's just a quick summary of Vesper theory using number 4 in that sheet to answer it. Still think it's a lousy question. I mean, it's a fair question if I gave you 10 minutes. It's not a fair question on a multiple choice question, in my opinion. All right, let's go to the next one I have chosen here. Let's look at number 5. Hybridization. Here I want you to turn to, and you should all have in front of you now, get them out if you don't already, these review sheets I gave you that I made up. And turn to the page. I want you to add something on there, actually. Turn to the last page, but the inside of it. It looks like this. Okay, I'm looking at this top part here. I want you to add a column right here. And that column I want you to add would be the bonds, like whether it's a single bond, a double bond, or a triple bond. The bonds with carbon atoms. Okay, so just add this thing on here. All right, so add the column, bonds, whether it's a single bond, double, in most organic molecules. Okay, if you're talking about a carbon compound, and if that's what we're talking about in this example question, this sample question we have here, it says it gives you this compound. It gives you basically, what's the name of that compound right there that it's pointing to in number 5? Pointing to. What is the name of that compound? Ethane. Yeah, we should all know that because we have more organic than most people who took the AP exam. All right. When I have ethane, whoops. When I have ethane, I have all single bonds, right? This guy. There's several ways to look at this. Why I made this chart up, and they can ask you what's the steric number. They could ask you what's the bond order. They could ask you is it single bonds. They could ask you is it sp2, sp3, and unfortunately, there's all those different ways of saying exactly the same thing practically. All right. You have to know, and you should fill in the rest of that chart underneath there, that, let me erase this part. The rest of that chart is filled in for you, with the exception of, okay, all these over here, all right, if it starts with sp3 down at the bottom, if it's sp3 and it's an organic molecule, they're going to be all single bonds. Okay, pretty much if that's what you have, an sp3 hybridization, to be single bonds. And if you think about it, that makes sense. Think about S and 3 P's means there's 4 things bound around carbon. When there's 4 things bound around him, okay, which means that's his steric number, all right? When there's 4 things bound around him, there's no room for anything else. That's all he's got, right? If it's sp2, that would be a double bond. That's what's in the next column. And if it's single bonds, it'd be sp1. All right, just S bonds are not going to happen with an organic compound unless you're bonding to, like H to H would be an S bond, something like that. But an organic, sp1, 2, or 3 would mean single, double, and, I'm sorry, I wrote single again, triple. sp1 is triple. All right. And again, you might want to look over those things because it talks there in the column right underneath that about sigma and pi bonds. If I have a guy like this, all right, think about it. All right, if I asked you how many sigma bonds are in this guy, what would you have to do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds. How many pi bonds? 1, 2, 3. You see? Okay, all that stuff tonight. Not tonight, over the weekend. If you want to do well, you're going to have to look over these charts and make sure you know all this stuff, including the memorization stuff, even on the front side. All right, so the correct answer to that, since they're all single bonds, that's sp3. The correct answer for number 5 should have been C, sp3. All right, let's look at number. Next one I've chosen is 6. 6 is a half-life problem, which we actually did quite a few half-life problems in Chem 1, but we didn't cover it in Chem 2 here in the second part of the year. But this is not a problem at all. This is a common sense problem. See why this is a common sense problem? By the way, the reason I chose these like 6 problems or 8 problems I'm going to go over, it's very simple. I put all your papers out, and these are the ones that were the most wrong. These are the ones that were gotten wrong by the most people. So I'm going over ones that chances are you didn't get right. Okay? This one you should have gotten right. Those other 3, I don't blame you at all. There's other ones, most of these other ones I don't blame you. But this is one I was really surprised by. There's a couple other ones that I thought maybe you'd do better on. It says the half-life is 2 hours, and it takes 12 hours to ship it. Okay, so 12 hours divided by 2 hours is 6 half-lives. Okay? It goes through 6 half-lives. So how much do you have to have if you're going to end up with 1 milligram? 1.0 milligram. Okay? If I'm going to end up with 1 milligram of this stuff, it will have cut itself in half 6 times. So in other words, if I double this 6 times, and just do that, what will I get? 1 times is 2, 2 times 2 is 4, 4 times 2 is 8. What do you end up getting? 64. Okay? That's all you had to do in this problem. That's a problem. And this is where I don't want you to spend on your multiple choice section, guys. Michelle, I don't want you to spend 20 minutes staring at a problem like that last one. Like I have a problem like that. Make your best guess. Try to remember as much as you can. If you find yourself doing the needed available shared and doing all that crap and writing those guys out for a problem like that, and you took 10 minutes doing it, you're not going to get finished. It's as simple as that. I recommend taking your best guess on a guy that you feel takes too much time to do. But my point is this. If you took a little bit extra time on some of them, it would be made up for by a guy like this. A guy like this, you recognize it takes you about 30 seconds to do. Anybody in 10, 30 seconds could do that problem, right? Now that you know what to do, 64, okay, this times it by 2 that many times. It's not that hard. All right, let's look at the next one. I got pick number 10. Now let's look at number 10. It says the delta G for a reaction has a negative value. Right off the bat, that tells me something very important. I hope you all remember, because I drilled it through your skull in almost every chapter, not just thermodynamics. What does negative delta G mean? Spontaneous, yeah. So what does that tell me about the reaction? Number one, the reaction is exothermic. A lot of people put that down. No. A negative delta H does tell me that the reaction is exothermic. And exothermic does favor spontaneity. But it doesn't necessarily mean, because it's spontaneous, it has to be exothermic. Because there are two parts to delta G. Delta G equals delta H minus T delta S, right? So you're all watching that. There's the entropy part right here, and there's the enthalpy part right here. If I've got a negative delta H, it is true, that favors to get a negative delta G. But a negative enough delta S could overcome that. All right? So remember the possibilities. I know he's spontaneous if I have those two possibilities, right? Negative delta H, positive delta S means that he has to be spontaneous. Okay? But in this case, right here, it doesn't say. It just says it has to be exothermic if it's a negative delta G. That's not true. The second one, the reaction occurs spontaneously at 298. That is the very definition of a spontaneous reaction for negative delta G. That's what it means. So that is a correct answer. Does it mean it's the only one? Not necessarily. Let's look at 3. The rate of reaction is fast. Yeah, guys, the one example I did, if you remember this, the one example I did when I started kinetics was the delta G for burning a diamond is like negative 365. I forget what the number was, kilojoules per mole. Why don't we burn diamonds? It's expensive. But besides that, it's very what? Slow. Spontaneity has nothing to do with speed. Kinetics is a totally different chapter. See, just because something's spontaneous does not mean it happens quickly. It just means that it will happen. All right, so let's go on to number 11. I just have 4 more to go. Number 11. This is another one of those problems that just drives me crazy that they would ask this. They give you this equation, okay? Watching this? They give you this equation. Nope. Oh, all right. 2SO2 plus O2 yields 2SO3. And I'm leaving out the states. All right. And it says you have 0.2 moles of SO2 and 0.20 moles of O2. Now, you can do everything right in this problem. I did it when I first did this problem, and I got it wrong because I forgot something. And it's a classic example of how these are trick questions, and they really are. A question like this is trying to gauge your understanding of stoichiometry and limiting reactants. Okay? And you can get all of this right, but for one little thing at the end, and get the answer wrong. Oh, by the way, it also gas laws, right? So the question says, it gives you a temperature and wants to know the pressure in the flask. Well, we know PV equals nRT, right? We know PV equals nRT. It wants to know the pressure, so P equals nRT over V, right? You all looking at this? You're looking at this, Abby? Really? We know this. The only variable we don't know, really, is N, moles. So I got to figure out how many moles are made from this guy. Well, the first thing I better determine is who's my limiting reactant. Can you tell from that who's the limiting reactant? Because that will determine how much of the product I get. Who's the limiting reactant? What will you run out of? What will you have excess of? Well, an easy way to do limiting reactants is just divide by their coefficient, right? If I divide by the coefficient, I get 0.10 here. I get coefficient is 1 here. I get 0.20 there. I have less of that. He's the limiting reactant. Okay? So now I know that he's my limiting reactant. That's nice. 0.20 moles. And that's what most people went. That's what I did. Plug it in for N. But there's your mistake. That will give you 0.20 moles of SO3, which is a gas. But in the same container, you only used up half of this. So there's another 0.10 moles of this guy who's also a gas. So you have to add those two guys together to get 0.3. 0.3 will be the least likely choice of those, A, B, C, D, and E, from anyone who had a small or a fair knowledge of limiting reactants and stoichiometry and ideal gas law. They wouldn't pick 3. They'd pick 0.2 or 0.4 over 3. But because you had a good knowledge of it, you actually get hurt by this. Because you did everything but remember there's excess of this, and this guy's a gas as well, so he'll add to the pressure in the container. Had this been a liquid, had this been a solid, guess what? You would have been absolutely right to use that. But it wasn't. It was a gas, and you had leftover of it, and so it adds to the pressure, and you have to add them in there. That's how hard that question is. Okay? All right, let's look at number... So the correct answer... I forget which one it was there, but yeah, B. There it is. Okay, a couple more I'm going to do. 21. Go to 21, please. (21) is another example of a very difficult problem because it gives you the order of the acid strength. What I would look at there is every one of those A, B, C, D all make sense because the stronger acid is doing what he's supposed to do. What does an acid do with his H? Gives it up. Look at E. Who's the stronger acid there? H, C2H3O2 is a stronger acid than the HCN. Yet he is accepting the H from left to right. So that's why that's the guy that doesn't make sense. Okay? That's the guy whose equilibrium comes to be less than 1. Less than 1 means not spontaneous. It would go the opposite direction or go more towards the other side. Last one I want to do is 22. And 22 and 25. 22, that's the second one that I was shocked that everybody didn't get right. Which two trials do you want to look at to see what the order is? Which two trials has somebody held constant? You can pick either two. You look at 2 and 3 for me. Look at 2 and 3. What happens there? 0.2 to 0.2. In other words, X stays the same, correct? What happened to Y between there? It went down by 1/2, correct? What did the rate do? It went down by 1/4. Okay, if you look at those numbers on there, you guys have them. Okay, if you look at those numbers on there, you'll see that this guy decreased, Y decreased by 1/2, yet the rate decreased by 1/4. So I now know Y is to what order? What order is he? Come on, if I double somebody and he quadruples, what order is he? Second. Okay. Now, look at trials 1 and 3. What happens to Y in trials 1 and 3? He stays the same. But what happens to X? Doubles. What happens to the rate? Stays the same. Remember doing these? We did an entire chapter on these. We did 2 or 3 labs on these. And we did multiple problems on these. So X we now know is to the 0 power, right? Since it didn't change. And I told you the one I did get wrong. I almost got this one wrong because sure enough, I'm looking for this. And what did I almost choose? I almost chose E, right? What is the correct answer? B, because X to the 0 power does not need to be in there. That was XY squared is E, and that's wrong because that's implying a 1. He is not first order, he's 0 order. If somebody's 0 order, he doesn't even show up in the rate law expression. He's just Y to the 2nd power. So rate would equal K, Y to the 2nd power. That's all you would have to do. All right, one last one to do. That's 25. All these are the ones you guys did the worst on. That's why I'm choosing them. Okay, it just wants to know nitrogen family of elements. Which things are true about it. If I'm looking at a periodic table at nitrogen, what family of nitrogen? The first thing you got to know is what's a family. I hope everybody knows by now. The family is. Let me get a periodic table up here. The family is a vertical group of elements. I had a bigger one, I thought, somewhere. I guess not. Ah, here we go. All right, so let's look where nitrogen is in this family. Okay? I'm looking at these guys right here. Excuse me, I can see it better. Looking at those guys right there. Let's read the first question on there. It contains both metals and nonmetals. Absolutely. All right? You don't have it, but I have it on mine. All right? The metalloids border that line, right? So, but even if I didn't have that, you should know bismuth is a metal, and antimony are metals. Okay, even though this guy is bordering the line. So it does contain nonmetals and metals. These guys on the left side are metals, they're nonmetals. It does contain that. The electron configuration of the valence shell is ns2np3. Well, let's look at that. Something S2, something P3. Would you expect that from this? Absolutely, right? Look where nitrogen is. He's in the P block, right? He's 1, 2, 3 over, right? In the P block, he would end at something P3. And if everybody in there will end in something P3. He'll end in 2P3, 3P3, 4P3, 5, because the rows, as you know, tell you the energy level, the highest energy level he's in. So that's correct. Where does that leave? The oxidation states. I looked at that one, and even I had to think to myself, well, I don't know every oxidation state of nitrogen, and it gives you like 4, -3, 0, +3, and +5. I know those exist, but is that all there is? I don't know. I'm going to leave that go to later, so I went down to D. Atomic radii increase with increasing atomic number. As I go down with increasing atomic number, 7, 15, 33, 51, would you expect these atoms to get bigger or smaller? Bigger, of course. So that's correct. So that brings me to E. The boiling points increase with increasing atomic number. That's a tougher one. Let's take a few seconds to talk about intermolecular forces. You may remember when I did a chapter on intermolecular forces, we graphed all of these. These 4 guys bonds with hydrogen, compounds with hydrogen. So HF, H2O, H3N, CH4, actually NH3, CH4. And then all the way down. And what we found was the boiling points rose as they went down, but there was a guy that was out of place in every one of them. The guy with the hydrogen bond was higher than you'd expect. Intermolecular forces get stronger the more protons, the greater the positive charge of the nucleus, the greater Coulomb's law. Basically, you're going to be able to have more induced dipoles, which are going to increase your charge, increase your attraction between molecules. So boiling point does increase as the atoms get heavier. You may also remember me talking about that with organic. My classic example there was I started with CH4. All these guys only have nonpolar bonds. Then I said, like, what about C4H10? That's butane. This is methane. Methane's a gas. Butane, he's kind of a liquid in that your lighters, but he turns into a gas real easy. C8H618. That's octane. That's like gasoline. That's a liquid. And as you get higher and higher, more and more bigger and bigger atoms, the more atoms you get, and the larger those atoms are, the stronger the intermolecular force. Both of those things are true. So that's why I had to go back to C and see that, well, geez, I don't know. I didn't memorize every oxidation state of nitrogen. I don't know if anybody in their right mind ever did. But I do know one guy that we used a bunch of times. Didn't we see in all of our, of course it had to be green, in all of our redox reactions? Didn't you guys have like NO2 a whole bunch of times? We got NO2 all the time. What's the charge on nitrogen NO2? +4. So that just proves that right there. Now, again, that's a tough question. You're going to get that done in 90 seconds? I don't know. Maybe not. But, and also it's tough because you had to understand intermolecular forces, periodic trends, a lot of stuff in there. But it's not an unfair question. It's just a tough question. All right, now I'm going to stop here because that's the end of that test.